Alright, so I just want to quick discuss the homework solutions a little bit. I'm going to post these shortly for AP Physics C. But there's some really good problems here that warrant looking at a little closer. So, Chapter 10, we had this plane landing on an aircraft carrier, right? So it has all this initial kinetic energy, and then spring catches it and slows it down. So it's going from kinetic into potential. I wrote a little backwards here. I said 1/2 kx squared at the end has to equal the 1/2 mv squared initially. Solve for the initial velocity. Make sure all your units are right. You get about 60 meters per second. Not a big deal. This one's a little bit different. Actually, let me just grab my book quick. All right. So that was chapter 10, number 29 there. This is one of the sneakier problems I seem to think. Let me see here. Chapter 29. Yeah. The potential energy diagram, right? This U-shaped thing. So I just want to talk about this for a second here. It says 20-gram particle released from rest at x equals 1 meter. So if it's released at 1 meter, right? I drew a line in the book. If it's released at 1 meter, that means it's all potential energy at that point, because if it's released, its kinetic energy is 0. So it's all potential energy, 4 joules of potential energy. And that means that the whole time this thing's moving, the total energy has to be 4 joules. 4 joules of energy total the whole time. All right? So over here, if it's 3.5 joules of energy at 2, that means it's a 1/2 joule kinetic. At 3, if it's 2.5 joules of potential, that means it's 1.5 joules of kinetic. At 4 meters, it's 1 joule of potential, so it's got to be 3 joules of kinetic energy. And then from there, the potential energy goes back up until you get to here, again, where the potential energy is 4 joules, there would be no kinetic energy. So it's almost like you can pretend the top of this graph doesn't even exist beyond that red line that I drew. It gives you the whole range, because if it was released at 0 meters, that would be it. If it was released at 7 meters, that would be its potential energy. This is a restorative force that would always try to bring it back towards 4 meters, because as it, remember, it's the negative slope of the line. So part A, will the particle move to the right or to the left? How can you tell? Well, you got to look at what's going on with the force, right? So at 1 meter when it's released, the slope of the line is negative. But remember, the force is the negative slope of potential energy versus position. So actually the force would be positive here. So it would accelerate to the right. But once it got to 4 meters, that slope of the line changes. And what would happen is it wouldn't turn around at 4 meters. What would happen is the force would start becoming negative, because the slope of the line changes to positive. Therefore, the force is negative. It would start pulling it backwards and slowing it down, so that by the time it got to 6 meters, it would stop and then accelerate backwards. And actually, this particle would oscillate between 1 and 6 meters. It would oscillate between 1 and 6 meters. It's like a mass on a spring, but it's normally a spring graph is nicely curved like a U shape. This has got some weird thing in the beginning, so I don't know what. Maybe it's a messed up spring. Maybe it's a deformed spring. I don't know. It's very hard to put physical situations on random potential energy graphs. So what is the particle's maximum speed? At what position does it have this speed? Well, its maximum speed occurs when it gets to 4 meters, because that's when the potential energy is the lowest. And potential energy is the lowest, it's going to have the most kinetic energy. All right, so you're going to see one of these on a quiz or test, one of these graphs here. I really like these. So then you just say, okay, so it's 3 joules. All right, it's 3 joules. I had to edit this because I didn't look at the graph when I did this the first time. I just said, okay, it's going to maximum kinetic energy is going to be when it's all kinetic, so it's 4 joules, but it's not. The minimum potential is 1 joule. Therefore, K max is actually 3 joules. So then I set that equal to 1/2 mv squared. Solve for the velocity when the kinetic energy is 3 joules. Great question. Part C asks about turning points. Turning points are not the turning points in the graph like you'd think of. Turning points in this case are where the object itself is turning around. So it's going to turn around when it has no kinetic energy. It's kind of like throwing something up into the air, right? It goes up, hits the top, comes back down. So it turns around when the velocity is 0. So that's happening at 6 meters or 1 meter. First, I didn't consider 1 a turning point because that's where it was starting, but when I looked at the solutions in the back of the book, I saw they considered that. So I said, oh, okay, so K equals 0 joules, V equals 0. So they're just saying it's, you know, it's going to oscillate, basically. Number 49 is this ski ramp problem. This is a big problem, right? Because it involves, this is AP type stuff, right? Where it involves conservation of energy, and then it becomes a projectile motion problem, right? That's why we haven't done many AP problems, because most AP problems draw from multiple areas of physics. It's not just kinematics. It's not just momentum. It's one AP problem will encompass all kinds of topics. So we need to use energy concepts to find V at the end of the ramp. Okay, so the UG at the top gets converted into kinetic energy and potential at the bottom, right? So at the bottom, off the ground a little bit, right? So mgh at the top equals mgh at the bottom plus 1/2 mv squared at the bottom. I'm solving for the velocity at the bottom. And when you do that, you get a kind of a cool result. You get radical 2g delta h. So you can always find the velocity of something falling. You know, usually h2 is 0, right? So we just do radical 2gh, but really, if you think about it, it's always the change in height that it's gaining energy from. So radical 2g delta h, about 21 meters per second. And then from there, it becomes a projectile motion question, okay? Now, what's crazy here in the book, they make you use the quadratic formula or the solve function in your calculator all the time. All right, I don't do that too often in class, but that is fair game. All right, so delta x would equal whatever the initial x velocity is, multiply the time. The initial x velocity is 21 cos of 30. All right, we've got the initial velocity there, so we've got to find the x component of that initial velocity. I just drew it as a cliff problem, right? The time to hit the ground, though, I don't know. I have to get that from the y direction. So delta y, 1/2 at squared plus v initial t. Be careful with your signs here, right? So it's falling down 3 meters, and the acceleration is negative. So you need to make sure you put the proper signs on these, otherwise you're going to mess that up. So negative 3 meters equals 1/2, negative 9.8 meters per second squared t. There's the y component of the initial velocity. It's positive because it's being shot upwards, right? So be careful with your signs here. Then I made this quadratic, and I have this really cool solver function on my calculator where you just put in a, b, and c, and it gives you the roots. So 2.4 seconds from my calculator, and that's just a very cheesy little calculator. I love it, though. So that 2.4 seconds goes back into the x equation. You get to 42 meters. All right? 71. This baby is my favorite problem, one of my favorite problems in this book. This is as close to an AP question that you're going to find in this textbook, okay? Those challenge problems, right? And what makes it a challenge problem is not the physics, actually. It's the geometry. And I've tried highlighting that fact to you guys before, that it's not the difficulty of the physics that makes a problem tough. It's often the geometry or the way you have to look at it physically. So I kind of drew before and after and tried to line up the heights to show you what's going on here. So this thing's going to fall down, hit the spring, and compress the spring. It's going to be all gravitational energy here. And then when the spring is compressed, it's going to be all spring potential energy. We want the zero height to be when that spring is compressed, right? What does that correspond to vertically, right? So that height here, right? That's going to be when the spring gets fully compressed. So I have to do this little trick here. I know it slides 4 meters before it hits the spring, so that would be the point where it hits the spring. And then it compresses the spring a distance x, right? 1/2 kx squared. All right, so 4 meters plus x is how far it's going to slide down the ramp. So energy is going from UG into US. So mgh into 1/2 kx squared. This height is the change in vertical height as it slides down the ramp. Now remember, this vertical height has to correspond to when that spring is compressed. So that's our zero location there, right? So I got to make a formula for the height. All right, so here's the height. That's what has to go in for h, but I got to write it in terms of x and 4 to make the algebra work. So sine of 30 equals opposite over hypotenuse, h over x plus 4. So that's x plus 4. And this is the AP level stuff right here. This is AP Physics C. This is what they do. They make you this crazy geometry, and you have to make a relationship up here, and then plug that back into the conservation of energy. So that's how they make conservation of energy hard. They give you some weird geometry where you have to figure out a relationship and plug it in. All right, so h is equal to x plus 4 times the sine of 30. Sine of 30 is 1/2, so I wrote it as x plus 4 over 2. So that's h. That goes into h, all right? So I have mgh equals 1/2 kx squared. Multiply both sides by 2, multiply both sides by 2. The 2's cancel, and you end up with mgx plus 4mg. So I distributed the mg through. All right, equals kx squared, mg, x plus 4mg equals 250 x squared. And now I'm just doing the algebra. And look at this. I get another quadratic. I'm looking for the root, right? I'm looking for x, how far the spring is compressed. All right, so look. I get a root. I had to use the sow function again to get 1.5 meters. All right. Which, was that right? I didn't even check. Oh no, my whole video will be fried if this isn't right. It seems kind of big, but I guess it's 4 meters is pretty long, so I mean, I guess that would make sense. All right, Harmon, what have you done? Have you done it right? Have you done it right? Number 71, chapter 10. Chapter 10, number 71. Uh-oh. Oh, no, yeah, 1.46 meters. Great, 1.5 meters. All right, so then over here, max speed when acceleration goes to 0. All right, so it's asking for then, when does it reach its max speed? Well, what you got to realize, when it first engages that spring, right, the force is going to be up the ramp on the block. That doesn't mean it's not still speeding up. It's going to speed up until that spring force cancels out gravity. I tried to draw that down here. So when it's going to, if you think about when it hits that spring, right, the spring force is going to start off very weak. Gravity's still going to be bigger, so it's still going to be accelerating down the ramp. It's not until that while the spring's getting compressed, once that spring force balances out gravity, then it's going to start slowing it down. And as it compresses further beyond that, it's going to slow down and stop. So when the spring force equals the x component of gravity, bringing it down the ramp, that's when the max speed would occur, when it hits that equilibrium. Otherwise, it's still accelerating down the ramp. Soon as after these two balance, it's going to start accelerating up the ramp and slow down. So FGX has to equal the force of the spring, mg sine 30. The x and y components of gravity, you got to get those quick, right? The x component is mg times the sine of the angle of the ramp. The y component is mg times the cos of the angle of the ramp. All right, FGX, FGY, you got to just know those finals. I don't want you thinking about that. The x and y components of an object on a ramp, you just have to do it. Don't think about it. Mg sine theta, mg cos theta for y. All right, that has to equal kx. Magnitudes here have to equal each other. I didn't put the negative sign on here. Anyways, you get about 0.20 meters. All right, on to chapter 11. Chapter 11, let me go back to the chapter in the book here. First problem was pretty straightforward. Determine the work done by each force, right? I thought this was, just kind of some practice. And we got these three forces, two pulling up and to the left, one the weight pulling down, and the object is going down, right? I think it says that. Yeah, second story winded to the ground. So the object is displacing down 5 meters. So I showed this in a couple different ways. Work is equal to the force parallel, component of the force parallel to the displacement multiplied by the displacement, right? So the displacement's delta y in this case. The parallel component is the y component of each force. So for work 1, it's 1,830 newtons times the sine of 60. Angles here is 60 on this side, so you got to do sine to get the y component times 5 meters. Now, you have to put the negative sign in here because the force is opposite the direction of the displacement. So the work in this case would be negative 7,900 joules. All right. Work 2, right? I did a little bit differently. I showed I put the whole angle between the force and delta y. And sometimes that's a lot, and if it's the whole angle, you always use cos. So 1295 times 5 times the cos of 135, all right, that gives us negative 4,600 newtons. So if you do it this way, all right, that's almost better, because here I would have had to make it 150. So I would have just done this times 5 times the cos of 150, and I would have gotten that directly without having to think about the sine. So the whole angle might be better. Then for work 3, 2,500 times 5 times cos is 0, because for gravity, it is pointed along the direction of displacement. So you get positive 1250. Now I have no clue when this period's going to end. I should probably pay attention to that, but oh well. We'll see what happens. So there you go. If you add these two up, look, you get to 1250, because it says it's at a constant velocity. So they made it work out right. 17, area under the curve, equals the work done. Pretty straightforward. The velocities, be careful. The first time I thought the velocity at 0 was 0, so I messed up. So the area under the curve, all right, 1/2 base times height. The height is the unknown variable, which is kind of unique. So you're solving for F max, which is the height of that triangle. 1/2 base times height equals 1/2 mv final squared minus 1/2 mv initial squared. You get a F max 8 newtons. Number 20, pretty straightforward. There's a potential energy function. Graph it. Take the negative derivative of it. You get negative 12y squared for the derivative. Then you just evaluate it at 0, 1, and 2 meters, and you get those forces. 38, kind of a pain because of the units, right? You got this potential energy graph. You got to find the slope of the line, but keep in mind this is in centimeters. So this is down 4 joules over 1 centimeter. So that's a slope of negative 400 joules per meter. All right, so that would be positive 400 newtons of force. You have to reverse the sign on all these. So 0 slope. This is a slope of positive 200, so that's a force of positive 100, so that's a force of negative 100. This is a slope of positive 400, so it's negative 400 here. So area under the curve from 2 to 6, which is kind of odd because, 2 to 6, the area bound is just right there, so it's kind of a strange interval to give it over, but oh well. I got negative 2 joules, 100 newtons times 0.02 meters. You got to make sure you put the units in meters. So negative 2 joules equals change in kinetic energy. Follow that through. You get a required initial velocity of 22 meters per second, because the work is negative, right? So the work is going to be taking energy out of the object. So it's got to start faster than it ends, because it's going to lose 2 joules of energy. All right, so it's just a quick talk through of the homework solutions. I'll post these both in the topic ASAP. Hopefully you guys notice. I don't know. All right, take it easy. What's going on here?